All right, so in this section, we're going to wrap up our discussion about limits. We'll be looking at section 1.5, where we will introduce the concept of infinite limits, which you'll see how that works. Sometimes the limit of a function is either positive or negative infinity. And then if we have time, we'll start derivatives, which I mentioned in the last section, is really one of the most important topics in all of calculus. So we'll finish this here and then we'll see how it goes. All right, anyway, so we'll start out by looking at an example of a function. And you can see that it has a vertical asymptote. The function is 3 over x minus 2. All right, let me just copy that into the notes. So the first thing you notice when you look at this is that clearly 2 is not part of the domain. X equals 2 would cause division by 0. So therefore, that must be an asymptote, a vertical asymptote of this function. Okay, so whatever it looks like, we know that x can never equal 2. And so the graph looks like this. So you notice how to remind you a lot of one we saw earlier, which is f of x equals 1 over x. Just as a point of comparison, you can see that in this function, which we've run into before, there is also a vertical asymptote. In that case, it happens to be the y-axis because that's where x equals 0. For the new one we're looking at here, 3 over x minus 2, the vertical asymptote occurs at x equals 2 because that is where we would end up with division by 0. Okay, great. Now here's what they want you to notice. If I approach x equals 2 from the left, notice how as I keep increasing x, the function is falling very, very rapidly as we get towards the asymptote. And in fact, it's heading towards negative infinity. On the other hand, if we approach 2 from the right, the opposite is happening. On this side of the asymptote, the function is increasing without bound, it's called, which means that this limit is positive infinity, or just plain infinity. So the same function can have two different limits like this. When we approach the asymptote from the left, the limit is considered to be negative infinity because you can see that the function continues to decrease and will continue to do so as we get closer and closer to the asymptote. And then coming from the right, it's the other way around. It's going up and up and up. It's increasing without bound, which means it's approaching infinity. And of course, they love their tables here. If you keep adding or increasing x, like I said, from the left, you notice how these numbers are getting very, very negative. If you increase from the decrease from the right, the numbers are getting very, very positive, very large and very positive. So that's why we end up with this. So we have a limit as x approaches 2 from the left of negative infinity, and from the right, it's positive infinity. So we call that an infinite limit. All right, so now here, it's a little bit different. Whatever this function is, here's our c. Actually, let me copy this so we can see it better. As we approach from the right, as x approaches c from the left, rather, sorry, from the left, clearly the function is increasing without bound, and so the limit would be infinity. And then if we come from the right, it's also increasing without bounds. So in other words, coming from the left or coming from the right, in either case, the limit is infinity. So in that case, we can say that the limit of the function as x approaches c is infinity because the two sides agree with each other. Okay, so this function has a limit as x approaches c of infinity because whether we're coming from the left or the right, either way, the function is converging to infinity. Now, oh, here's another interesting one. F of x equals -1 over x minus 1. That's um, -1, yeah, over x minus 1. And again, you can see just by looking at this function, the domain will not include +1. Okay, so that means we're going to have a vertical asymptote at x equals 1. So the function looks like this. Okay, so now if you notice, oh, this is interesting. The negative in the numerator changes the behavior of this function compared to, let's say, remember, we go back to this function, the inverse function. You notice this time we have the reverse in the sense that, actually, I'll tell you what, let's go back to Symbolab and draw two different functions so we can see this better. We'll start with 1 over x. Let's try that again. All right, so we've seen this many times before. Let me just grab a picture of it. You know what? I didn't even notice that until now. Over here on the right, it says, "Hi, ask a question about y equals 1 over x." I think that everybody's getting on this AI bandwagon. And so I guess they're trying to expand the capabilities. Maybe it was always there and I never noticed it. But I guess we could ask it further questions if we felt so inclined about the properties of this function. See, sometimes this thing works and sometimes it doesn't. I don't know what's going on. I guess it's just like, sorry, I don't want to work today. It's a perfect metaphor for technology. It works when it wants to work. Okay. Oh, wait a minute. This time it actually worked. Oh my God. All right, here we go. So that's 1 over x. So how would it change if I replace that with -1 over x? This is what we're interested in. This is what I was hoping we would see. Okay. So in other words, they're symmetrical from left to right about the vertical axis. In other words, they're symmetrical about the asymptote. So let's grab a picture if Snagit will allow it. So you can look at them side by side. not sure if there's enough room to show them from left to right, but we'll try. There, I think we got it. Well, that'll have to do. Okay, it won't let me move it around any further. So I just wanted you to see how, even though we still have the same vertical asymptote, what's changed here is that here, the limit from the left is negative infinity. The limit from the right is positive infinity. Okay, but then in the second graph, it's the other way around. Okay, so you can see just by looking at it, if we come from the left in this case, the limit as x approaches zero. From the left, this time it's positive infinity. And from the right, it's negative infinity. And of course, visually, you can see that they are mirror images of each other. It's like we took a big mirror and we reversed the function when we went from 1 over x to negative 1 over x. Okay, so that is why when we come to this case, negative 1 over x minus 1, you can see it looks like this one, except the vertical asymptote is 1 instead of 0. Okay, so in this case, as we approach from the left, we have positive infinity, and from the right, we have negative. Okay, so we don't have like a limit for the entire function because these are different from each other, but we do have a limit from the left and a limit from the right. Okay, so now what else do they want us to see here? Yeah, so in other words, the limit from the left is infinity. The limit from the right is negative infinity. And oh, here we are. So they're going to formally introduce what a vertical asymptote actually means. It's a vertical line where the function gets very, very, very close to it, but never quite reaches it. Okay, so we've run into this several times before. Now this one is interesting because it has two asymptotes, and that's because there are two values of x where we would have division by 0. Okay, so it may not be obvious when you first look at this function, but it will show why this is happening. Yeah, and okay, so they're showing it to us here because you can see that the denominator can be factored out into x minus 1 times x plus 1, which means that the domain cannot include either negative 1 or positive 1. So that's how we write that in interval form. And so this is the graph. Let's copy that. And the two asymptotes again are x equals negative 1, x equals 1. You can see that depending on which structure we're coming from, we're going to have all in either positive or negative limits. The only thing that's different now is that there's two that we need to contend with. So, for example, here, oh, whoops, it's h. Sorry, what? That will give us positive infinity over here. As x approaches positive, oh wait, sorry, I did this wrong. This is negative 1. It's negative 1 from the left. Okay, well, here this is positive 1 from the right. And you can see that would be also positive infinity. Then here, bounded between negative and positive 1. So the limit Now here, it's interesting here that in this part of the curve, you can't actually approach -1 from the left. It has to be from the right. It's coming this way. Uh, and that means that this one is negative infinity. Coming from this side, it's the same thing. So, wait a minute. Yeah, that's right. Hold on a second. I did something wrong there. That's better. Okay, so in other words, -1 from the right is negative infinity, and +1 from the left is also negative infinity. Okay, so it's a very complicated function. Um, and of course, because it has two asymptotes. Okay, now here what they're showing us is what happens if you encounter a situation where we have two functions where in one case the limit is infinity or possibly negative infinity, and the other one is a constant. Okay, so for example, here with the sum property, whatever happens if you're at no matter what L is, if you're adding infinity to it, the sum will be infinity. If you're subtracting, it'll be the same thing. The product will be infinity as long as L is positive. If L is negative, the product will be negative infinity. And the ratio, as long as the constant is on top, will be equal to 0. Okay, so in other words, when we start doing more complicated limits, it'll be helpful to have this information right in front of us. Okay, so now obviously, now both of these were infinities. Adding them or subtracting them will leave us with infinity. But if one of our functions has a constant limit, the other is infinity, then we have to follow these rules. Okay, what do they want us to do here? Oh, all right. So like here's an example. So now the limit of this expression be rewritten in the following ways. We know from the previous section. Whenever x squared, by the way, looks like this. You can see it has a vertical asymptote is 0. Not that that's the best drawing in the world. Actually, let's go to simple there and let it do a proper job of that. Yes, that's much better. That's a real graph. But anyway, because it's 1 over x squared, you're still going to have an asymptote at 0 because you obviously can't divide by 0. But the difference is that there are no negative values. The range consists only of positive values. So the entire function is in the first and second quadrants, which is in here. So what this indicates is that the limit as x approaches 0 from the left is positive infinity, and so is the limit coming from the right. So we can conclude that the limit of this function is infinity. Okay. Now, this is going to come in handy. This result will be very, very useful throughout California. Actually, it may not seem so important, but it really is. The idea that the limit of something like this, as x goes to zero, is infinity. So that means that the sum of these two can be done like this. You got one plus infinity, and as we just saw from all those properties, we have infinity. All right, so that kind of makes things easier for us. Now, if you want, what we could do is graph this entire function and see how it looks. Yeah, I mean, it's not very different. Essentially, what's happened is um, the horizontal axis, if you notice from the previous graph, um, this function actually has two asymptotes. The vertical asymptote we know, but the horizontal axis is also an asymptote, okay? Because the function can never actually reach zero. So this one has a horizontal asymptote at one. So in other words, you're basically taking the same graph and shifted it up by one. So therefore, its behavior is going to be very, very similar. It's going to have a limit of infinity, and we look at it. The difference is where do we find the horizontal asymptote? Now, and of course, here's other examples. They're just showing us the same thing. They're showing us how to combine, create limits when we have a constant plus an either positive or negative infinity. Here's an interesting one. We've got this ratio. Now we do know that direct substitution will lead to division by zero. So whatever this function is, it definitely has an asymptote, vertical asymptote at 14. Why don't we show ask Symbolab to show it to us? Oh, I almost forgot. It's a limit. What am I doing? Limit as x goes to 14, 14 plus actually, meaning from the right of the ratio of x minus 3 and x minus 14. So, oh, actually, I just realized, no, no, no. I will let it tell us the answer. I really wanted to see the graph. Okay, let's try that. Okay, so there's an asymptote at 14, as you can imagine. And you can see now we're approaching 14 from the right. So therefore, it must be the case that the limit is infinity. You can see just by looking at the graph. As we come from the right, the function is increasing without bound, and that means the limit is infinity. So the correct answer is infinity. All right. Oh, actually, I just realized that's it for this section. So we are ready to at least introduce the concept of derivatives. So this is a big step forward, let me tell you. Um, because like I said, this is going to be one of the most important topics in all of calculus, derivatives. In fact, Isaac Newton invented calculus for the express purpose of explaining the behavior of his laws of motion, if I'm not mistaken. So differentiation is in principle, a fairly simple idea because it represents the response of one variable to a change in another. So we're going to start by looking at, let's say, this graph. Okay. Um, let's see what they're getting at here. You notice how it says use a graphing utility. I think they mean like the TI-84, but since we have Symbol Lab, we might as well use it. Just find some way to do this. In this day and age, there's plenty of ways of getting this graph. Um, Probably, I'm guessing ChatGPT could probably take care of it, but I don't really know anything about it. I probably should learn, but I've got so many other things I need to learn. Yeah, that have to come first. All right, 2x cubed minus 4x squared, plus 3x minus 5. All right, let's see. Now, of course, it's a cubic function. It's going to have a very unique shape. Okay. So yeah, after you've gotten used to seeing all these different functions, there's a certain way it has a tendency to rise and then it slows down at some key point and then it starts to rise again very, very quickly. This is a pretty classic example of a cubic function. So let me just grab a picture of that. All right, let me make a note of what this function is. All right, so that's the function. Now they want us to do what? Graph. Well, this is interesting. They want us to graph y equals x minus 5, 2x minus 5, and 3x minus 5. Which of these appears to be tangent to the graph at the point 0, negative 5? Hmm. Okay. So in other words, here's what we're looking for. We're looking at the equation of the line just touches the function at that point. Now that's a very steep line. I would be inclined to think that it would be this last one. Ooh, well, they didn't get our answer. That's interesting. So we can do now, it's been my experience with Symbol Lab that it doesn't seem to work well when you try to ask it for more than one graph at a time. For cases like that, I usually lean on Desmos. Maybe I find the instructions that come with Symbol Lab are just not very good. And so let's try it with Desmos. So I'm going to try my idea that this function, qx squared, a cube rather, minus 4x squared plus 3x minus 5 has a tangent at Y equals 3x minus 5. That would be my guess. And well, what do you know? It looks like I nailed it. Okay, so in other words, here's the point 0, -5. And you can see that this is in fact the tangent line to that function at the point of interest, which is 0, -5. Now, this will prove to be very important. Um, but I guess they've decided to go on and show us some more theory here. So here's what they're going to try to do. If you had a curve of some kind of a function, the logic behind what they're about to do is this. Say here's some random function. And I'm interested in finding the tangent, let's say here. So I could start with the secant line. And the slope of the secant line is, of course, the change in the uh, y variable, or in that we're going to call it f of x here, divided by the change in x. So we're going to have, in other words, you remember learning about this in high school. It was sometimes called the rise over the run. So basically, it's nothing but the slope of a straight line. Okay. So this part down here is defined as delta x. Okay, now here's what they're trying to get you to see. Suppose that I keep x1 where it is, and I choose another x2, which is a little bit closer to x1. For example, and if I continue to do this, and I get closer and closer, meaning that this delta x is shrinking, eventually the secant and the tangent will coincide with each other. That's really what we're aiming for. Okay. So the logic behind what's about to follow is that we can find the slope of the tangent line by starting with the secant, and by continuously shrinking up the difference between the 2 points, the two x values, eventually the two will match. The two will converge to each other. In other words, we're going to take a limit. The limit, as delta x gets closer to 0, will give us what we're looking for. So to find the slope of a graph, f of x equals 2x minus 3. Now this c, so with here, yeah, in their graph, I think the c is the x coordinate. What I was calling x2, they're calling it c here. Okay, so we'll use that notation from now on. The x coordinate will be c. And we're gonna, you can see, well, it's harder to see because these are very small. Let me copy this into our notes. But they're doing the same thing. They're trying to show you what happens as we get closer and closer. delta x is shrinking, and eventually this secant line coincide with the tangent line at that point, C f of C. Okay, so this is what they're getting at. Now, how do we prove that? Well, what they're going to have us do is this. Um, let's see. Let me see if I can draw this. So C is the first value of X. These are the two endpoints. C is the first value of X. C plus delta X is the second endpoint. Um, so that means that this is f of C, this is f of C plus delta X. The slope of the tangent line, I'm sorry, the secant line, the change here divided by this change. Now, the difference between the horizontal coordinates is delta X by definition. Okay, so we just need the delta X here. So what they're going to tell us is that as we keep shrinking the delta X, we're going to eventually end up with the slope of the tangent line that just touches this curve at point C. And this is what we're interested in. So we're going to take the limit okay, great. Now, of course, we can't actually do this calculation without knowing the function. So they're going to give us the function 2x minus 3. C is 3. Sorry, no, it's 2. Okay. So we have to be a little careful here. First of all, what is f of C plus delta X in this case? So what that's saying is wherever you see an X in the original function, replace it with C plus delta X. But C is 2. So you're actually going to write 2 times 2 plus delta X minus 3. Because this is C plus delta X. F of C means you're replacing all the X's with 2's, which is 4 minus 3, which is 1. So the ratio you'll have is this. Okay, so we've replaced our f of c plus delta x and our f of c. Now we just have to do some algebra and then we'll take a limit. All right, here we go. So this is a particularly simple case because we're trying to find basically trying to find the slope of a straight line, which means it'll be a single constant. Drop out, so we're left with 2 delta x over delta x. Oh, well, it's just 2. Okay. Now, I don't know if they have a graph for this or not. Oh, they do. All right. So now, of course, because the original function is a straight line, no matter what point we chose, the slope of the tangent line is going to be 2. It has to be. Okay. So no matter what point, no matter what the c was, we were going to end up with the same result. And you can see because everything dropped out, you can see no matter what was going on in this function, we were always going to end up with 2. Now, we can't, well, they're saying us telling us to avoid having vertical tangent lines because they would have an undefined slope. Yeah. Okay, so now we're going to start by looking at the actual definition of a derivative, and you'll see that it is in fact based on limits. So this is the formal definition of the derivative of a function. And so let's copy this into the notes. And so you can see that what we're looking at is a function. And here, x plus delta x. Here's f of x, f of x plus delta x. And the difference between these two is delta x. So in other words, what you're seeing here is simply the slope of a tangent line between these 2 points in the limit. And that's because in the numerator, we have change in y, and the denominator with the change in x. So we're going to start with an example of this. Now, unfortunately, this definition can get very, very messy, but we won't be doing a whole lot of these. Fairly soon, we'll be looking at a series of rules that we can use to calculate derivatives without having to lean on this definition every time. So while you're watching this happening and you're saying, wow, this takes a long time, it's just to get us to understand what derivatives are. Once we're past this section, we'll be able to use the rules. All right, so here's our, oh, by the way, I do want to mention here, as a point of notation, the derivative can be written in actually several different ways. We can write f prime of x sometimes it's written like this, dy dx. Dy is an instantaneous change in y. And of course, that implies that dx must be an instantaneous change in x. And each of these individually is known as a differential. Okay, these are referred to as differentials. Okay, what other notation do we have? Well, sometimes you see y prime listed. There's a couple of others which you don't see quite as often. D dx of fx. And occasionally you also see this one dx of y. They all mean the same thing, but most of the time you're using the first two. And so the one you'll end up using is usually just a matter of convenience. Okay, so anyway, so let's look at our first example. So here's a function, and we'd like to calculate its derivative using the definition, meaning we're going to take the limit of this expression as delta x goes to 0. All right, so the derivative f prime of x will therefore be the limit as delta x goes to 0, f of x plus delta x minus f of x, all divided by delta x. And again, you can see what we're looking for is the slope of a tangent. Okay, in the limit. So now here's where it gets very messy. All right, potentially at least. What is exactly the meaning of f of x plus delta x? Well, you go at your original function and you replace all the x's with x plus delta x. So here you'll have that. Okay, so that will be this term, f of x plus delta x. Now, we have to evaluate that. Now, in this particular case, that's going to be a little bit messy, but we can do it. We'll start with this x plus delta x cubed. So probably your best bet is to multiply x, start with x plus delta x squared, and whatever result you get, multiply that by x plus delta x. All right, so I'm going to lay it out like this. There's many different ways you can multiply two expressions like this. And then what you're going to do is basically multiply all the different combinations. Here you'll have delta x squared. You multiply these terms, you'll get x delta x. Over here, you get, again, x delta x. And then finally here, you get x squared. Add them up, and this is the result. Okay, so this is the result of doing this, x plus delta x squared. But we need x plus delta x cubed. So in order to get to that point, we need to multiply this result by x plus delta x again. Whatever we get here will be x plus delta x cubed. Right? So this is going to take a while. Delta x cubed, 2x delta x squared. Here we have x squared delta x. Okay. Then when we multiply x by these terms, we'll have x delta x squared, x 2x squared delta x. And then finally down here we have x cubed. Add these up. Okay. So that was a lot of work. But remember, we don't just need f of x plus delta x. That's what we just calculated. We also now need to subtract the original function from that. Well, actually, no, I'm sorry. We that all we did there was x plus delta x cubed. We still need this part. Okay. So in other words, the numerator of this expression. Remember, we saw earlier on that f of x plus delta x equals this. In fact, why don't we copy it? Let's do that. It'll be a little quicker. So in other words, what I just did was just the first part. we still have these two terms. We have 2x plus 2 delta x. Okay, so this entire expression is just f of x plus delta x. So if you look at this formula again, what we have to do now is subtract f of x for our numerator. So look at this. Yeah, it would be helpful if we could combine some of these terms, but it doesn't look like it. So original function was x cubed plus 2x. All right, so well, this helps a little. We'll get some cancellations. These two will drop out, as do these two. Great. All right, so that means the numerator of this expression is going to be the denominator is delta x. And now you can see every one of those terms in the numerator has a term in it, a delta x term. So there'll be some cancellations that'll make things a little bit simpler for us. Great. So remember, what we have to do now is take the limit of this expression as x delta x goes to 0. So therefore, combining all this information, actually, I'll just grab the whole line. Okay, so for that, we need this part. Again, 3x squared plus 3x delta x plus delta x squared plus 2. Now, taking this one will be easy because all we're doing is the method of direct substitution. And then you'll see that our final result is and we're done. At long last, we're done with that ordeal. Okay, so you can see that was a lot of work. But like I said, we'll be exposed to a lot of very powerful rules that will enable us to calculate derivatives directly without necessarily, unless we want to, using this formal definition. But it's important to understand what we're actually doing when we take derivatives. We're looking for the slope of a tangent line, and we find that by taking the limit of the different distance between 2 points as they get closer and closer to each other. We end up with the tangent line to the curve. And so that's what we mean by the derivative. All right. So what's next? So now we're going to look at some more theoretical results. And then We're going to see the relationship between continuity and differentiability. And then I suspect, although I don't have it open right in front of me, we're going to dive into the rules of differentiation. Let's just go open up 2.2 and see what's coming next. All right, let's get that open. Oops. The basic differentiating rules and rules rates of change. That's what I figured. Okay. So this is where we get to learn all these different powerful rules. And there's quite a few of them, but we'll get used to them very quickly. And so this is where we'll pick it up next time. All right, I'll see you then.